For the first question, isn't it supposed to be negative, like the first one?
The one for the equation of the tangent line?
Yes.
We will go over it. Let's see. 4xy minus y squared equals 3. All right. You're being asked to find the equation for the tangent line at this point. So when you're doing the product rule here, group together the 4x and then the y can be g. So you'll have f and g. F prime in this case will be 4. G prime will be dy dx. So you're taking f prime g plus f g prime. Oh, sorry, I forgot the rest of f. F prime g plus f g prime minus 2y, don't forget your dy dx, equals 0. I'm going to leave my dy dx's over here and move the constant over. So let's see, if I'm leaving the dy dx's here, that means I have 4x minus 2y, and I'm moving the 4y over to the other side. Change the side, change the sign. And then you get dy dx is negative 4y divided by 4x minus 2y. And you will evaluate that at the point 1, 3. So that's negative 4 times 3 divided by 4 times 1 minus 2 times 3 is negative 12 divided by 4 minus 6 is negative 12 divided by negative 2 is positive 6.
I put 4y instead of negative 4y. So that's why I got
Oh, I see.
negative 6.
I
Yeah.
ended up getting a negative slope. Okay. Okay, good to know. So we figured that out. I'll just finish it since I'm over here. Y minus y sub 1 is m times x minus x sub 1. And then y equals 6x minus 6 plus 3, and y equals 6x minus 3, which hopefully, yeah, that should have been, I don't know. It's giving me like the preview, so I don't actually have the answer in here in the preview. 6x minus 3 was accepted as correct. Okay, other questions?
Can we look at?
Oh, go ahead.
Can we look at the second problem?
Sure. Let's see. Oh, now I'm not in the preview anymore. It's really bizarre. It's like I can't actually preview the questions unless I actually like fake take the quiz. There's got to be a better way. Let's see. Like even, I mean, I can go to. Who cares? Let's just try to do it this way. Fine. Mm-hmm. And I don't think I had these shuffling on this one, so it looks like you had find y prime for y equals e to the 1 over x squared. All right, so rewrite this one as e to the x to the negative second power. And then when you take the derivative, you're going to have y equals e to the u of x. So you're going to use the chain rule. The derivative is going to be e to the u of x times u prime. So you're going to take e to the x to the negative second power and multiply it by the derivative of x to the negative second power. So negative 2x to the negative third, negative 2x to the negative 3. And then you can rewrite this however you see fit. Negative 2, you can rewrite your e to the x to the negative second the way it originally displayed. I think that's how I had it display. And then write x cubed in the denominator. Let me see. Is that what I did? Negative 2 over x cubed. Yeah, it looked very much like this. Other questions on that one? And technically, you didn't have to rewrite it in this way. I just picked that way for the quiz. And I tried to be consistent among the answer choices, so I sort of built the other ones the same way. I graded your exams between last night and this afternoon. For the most part, they were very good, better than last time. They weren't all that great, but it is Calc 1, so I don't expect them all to be that great. But there were definitely more A's this time, more B's, more C's. More people passed, for sure. So that's good. I did put the key up for you to peruse. I already put the office hour notes up from today, too. I did that while you were taking your quiz. So those are up there, too. During the office hour today, I went through a bunch of WebAssign problems. I went through 6, 9, 13, 10, and 19. So the notes are up there on D2L. That homework's due tomorrow. Now, we're going to cover 3.3 tonight and then a little bit of 4.4. Of all the 4 sections we're covering in Chapter 3, Section 3 is the shortest. So 3.3 is going to be the shortest section we're going to be doing in this chapter. Section 4 is a little longer. So I'm going to start Section 4 tonight, which is derivatives for logarithms. And then I'm going to finish it in an asynchronous lecture for you, which I have to record tonight because I have no other time to do it. And I don't want to delay it too long because you'll want to look at it and study it, even though your test isn't until Wednesday. I still don't want to wait too long. But it's gonna be up late. Do you know why? Because tonight it's supposed to be like 63 degrees when we get done, and that's running weather. I don't like to run when it's more than 70 degrees, but tonight it's like the prime temperature. So I'm gonna do that after I put my kids to bed, and then after I get back, I'll be totally jazzed and ready to record for you an asynchronous lecture finishing up 3.4 and anything that you are required to know for your exam next week. So remember, your test is going to cover 3.1, 3.2, 3.3, 3.4. I'm going to write it down to remind you. Test 3 is going to be on 7/7, which is Wednesday. It's going to cover 3.1 through 3.4. I know it doesn't seem like a lot, but there's a lot that has gone on with these derivatives. So we'll have that. Remember that you have no class on Monday, July 5th. So someone asked me last night before the end of class when your homework was going to be due for 3.3 and 3.4. So anything I covered tonight, I feel like it's kind of silly to have it due Monday if technically Monday's an ECC holiday and if your test is until Wednesday. So your 3.3, 3.4 homework will be due on Wednesday. the day of your test. So, so you have a little bit of extra time there, but don't wait too long. I do still want you to enjoy your holiday weekend, but don't wait too long. Yeah, so that's kind of my plan going forward. And since we have a test on Wednesday and we'll be starting chapter 4 on Thursday, you're not going to have a quiz Thursday because there would be nothing to quiz you over. So no quiz Thursday, 7, 8. It just doesn't make any sense. So technically you have no quizzes at all next week because we don't have class Monday and we would have nothing to quiz over Thursday. All right, I'm trying to think if there's anything I forgot. I don't think so. Anybody have any questions?
Are you going to be doing an office hour on like next Tuesday or something?
Yeah, so I'll probably do it Tuesday. I'm gonna have to discuss with my husband. It would probably be at like 5 if I did it. Although I hate to have an office hour at 5 when class technically is at 6 because it might not fit everybody's schedules. I'll let you know though. If I did an office hour on Tuesday, I would probably do it around 5. That's probably what's going to work out best schedule-wise. I'm going to write that down as a possible office hour Tuesday, which is the 6th at 5 p.m. But I'll let you know. But I'm going to keep that in mind. I think Tuesday would be the best day. Sunday, I'm going to be out of town. My sister had a baby like months ago, and I haven't even gone over there to visit the baby. I mean, they live in Indianapolis, so it's not like she's 5 minutes away. So I'm doing that this weekend. So I'm not going to be in town until like later Sunday night. And then Monday is technically an ECC holiday, so holding an office hour is kind of weird. So if I did it at all, it would be Tuesday.
I have a question.
Yes.
Are we gonna have like a test review thing?
Oh, like on WebAssign?
Yes.
Okay. I'm going to get my stickies out. I'm going to put a note in here to post WebAssign test 3 review. It's going to be optional as always, but it'll be there for you so that you have a little bit of extra practice if you need it. Oh, one other thing I was going to mention is something I was going to add to my sticky notes. Post midterm grades. Your midterm grades are due Monday at 7 p.m. So I'm going to include in your midterm whatever you've done so far through today's quiz, which means I also have to upload your WebAssign scores. I have to go through and enter them, your WebAssign scores from chapter 2. I'll probably just leave it through chapter 2, even though you had 3-1 that was already due. I'll probably just leave that off. It's really not going to affect your grade anyway. But the midterm grades are due Monday, so I'm going to post that through the test I graded today in all of chapter 2. If you are not passing, they used to send home a letter. I don't know if they still do that. For those of you who still live with your parents, just a heads up, I used to have students all the time just be like, oh my gosh, we got this letter at my house and now my parents are freaking out. It's nothing I control. I enter your grade, it is what it is. I would say 85% of the class probably ends up with their final grade being the exact same as their midterm grade. Those really don't fluctuate that much. Every once in a while I'll see someone that goes from an F to a C, or someone that goes, from a C to a B or something. But keep in mind that your midterm grade is probably not going to be that different from your final grade. So be thinking about that as you head into the drop date. And I never want to encourage anyone to drop, because I had a student once who was like, she kept telling us to drop. No, I didn't. One time I forgot to remind students, and then I had a student really mad at me that she wanted to drop and missed the date. She was like, why didn't you tell us? That's why I keep talking about it all the time. So your last date to drop with a W is July 11th, 7/11. It's in your syllabus. Just keep that date in mind. So if you feel like you're not going to pass and you just kind of want to check out and be done with it, if you want to get a W, you have to do it by July 11th. But if you know that, well, I might have to take this class again in the fall, I still feel like I'd be better prepared if I stayed in for the summer, even if I don't pass, that's fine. Like, I'm not telling you to drop. I just want you to be aware that if you would like to get a W, you must do it by July 11th. Otherwise, if you don't pass, if you drop, you'll get a WF. But if you just don't pass, you'll get whatever grade you get. So I'm going to remind you of that as the date draws closer. I was putting my calendar together today and realized that our class ends in exactly 5 weeks, because today's Thursday. But we actually only have 4 actual weeks of class left. And after tonight, we're pretty much halfway done because we don't have class on Monday. So, I mean, this is going to be over before you know it, which might make you sad, as it makes me sad. All right. Anything else before we get into derivatives of inverse trig functions? Do you guys hear all the piano playing downstairs? If it's really annoying, you can let me know and I'll have him stop. My son's taking piano, which is awesome, but it's very loud. Okay, excellent. I never know what people can hear. Sometimes there's screaming in the hallway and people are like, yeah, that was loud. One day he'll be playing like trumpet or something. Like my brother used to play trumpet. Man, I'm so loud. I would complain to my mom all the time and be like, ugh, does he have to do this all the time? It's so loud. But she was like, yeah, I pay for this. He has to practice. It's true. All right. 43. Derivatives of inverse trig functions. Okay, so I'm going to give you some new derivative rules. There are going to be 6 of them, but very similar to how I gave you 6 rules for derivatives of trig functions, you're going to find that the derivative rules for inverse trig functions have the same pattern, where the co-functions are going to be very similar to the originals, just with negatives. So really, if you know the original function, then getting the co-function derivative is going to be very straightforward. All right, so let u be a differentiable function of x. So I'm going to give you 6 of these. The derivative of the inverse sine of u of x is going to be u prime of x divided by the square root of 1 minus u of x squared. By the way, your trig book might not have used this notation for inverse sine, and I don't remember which notation I used on the algebra review. I actually just put that packet away yesterday. It was sitting out for so long. I don't have it at my disposal. you might have seen the notation arcsine u or cosine u. So this just means inverse sine. Every book is different. You might have, I mean, I kind of like this notation better. Students like it better just because it's a little bit faster to write versus arc. I mean, if you write arcsine, it's just a couple more letters. It's up to you though. If you want to say arcsine, that's fine too. If I occasionally say arcsine instead of inverse sine, I just want you to know what I mean, because sometimes I just use them interchangeably. They're the same thing. But I mean, if you're not sure what I'm talking about, this means sine x. So same thing. They are synonymous. Okay. The derivative for the inverse tangent of u of x is u prime of x. So again, we're just keeping that u prime in the numerator. Now for the inverse tangent, we don't have a radical in the denominator, and we're going to be adding. So we have 1 plus u of x quantity squared. Now for the inverse secant, again, you're going to have u prime in the numerator. And this one's going to look similar to the inverse sine. The difference is, well, there are a couple differences. You are going to have a factor of u of x in the denominator in front of the radical. So you don't have that with the inverse sine. Then you're going to switch the order of subtraction. So instead of being 1 minus u squared, you're going to take u of x quantity squared and subtract 1. So nothing too major, but you know, understand the differences between the two. And the inverse tangent is no radical addition. And you'll just have to remember the order of subtraction there, but it's open note, so you really remember anything. Okay, now, like I said, for the co-functions, you've got basically the same situation going on. The inverse cosine of u of x is just negative u prime of x divided by the square root of 1 minus u of x quantity squared. So everything is going to be exactly the same, except it's just going to be a negative u prime in the numerator for all of these on the right. So that means for the inverse cotangent of some function u of x, you have negative u prime of x divided by 1 plus u of x quantity squared. And then for the cosecant, the inverse cosecant, I should say, negative u prime divided by, again, we have this factor of u of x multiplied by the square root of u squared minus 1. If you want to put a box around these or highlight them, it's not a bad idea. You do want them to stick out so that you can find them easily. Box around mine. So we're going to find some derivatives. We're just going to focus on using the formulas first and then sort of working with them in conjunction with some other things that we've learned in this chapter and the last chapter. So we're going to work on using this function, with these functions with the chain rule, with the product rule, maybe with the quotient rule. And then we'll talk about how to use these with implicit differentiation. Okay. Let's get going on these. Example 1, find the derivative. So the first function we're going to look at is y equals the inverse cosine of 3x minus 1. Now, if you're trying to sort of relate this back to your definitions, all of the definitions had u of x in them. In this case, u of x is going to be this inside function 3x minus 1. So when we take the derivative for the inverse cosine, remember it's going to be a negative derivative, and we're taking negative u prime in the numerator. So negative, and then u prime is the derivative of 3x minus 1. So that derivative is 3, so our numerator will be negative 3. And then we're going to divide this by the square root of 1 minus our function u squared. And we're going to simplify this, not like too crazy, but we're definitely going to simplify it down a little bit. Sometimes students find these derivatives to be strange just because you started out with an inverse trig function and then you ended up with a derivative that had no trig at all in it. That's okay, that's supposed to happen. So if you feel like that's weird and like, oh my gosh, what happened to the cosine? It's gone. It's not supposed to be there. When you take the derivative of an inverse trig function, there are no signs of trig at all in your result. So when we simplify this, we're not going to get too crazy, but I definitely want to square this binomial. So 3x minus 1 times itself is 9x squared, and then you have minus 3x is minus 6x plus 1. And then just take 1 and subtract that off. So when you do that, when you distribute the negative, you'll get the square root of negative 9x squared and then plus 6x. And the 1 minus 1 will cancel. So those will be additive inverses. And you will be done at this point simplifying the derivative. I don't need you to factor anything out and get real crazy. Just let it be. Honestly, WebAssign would probably accept this on a test. I would want to see this. Most of the points would come from here, but the last 1 or 2 points would come from simplifying it. And that's it for A. Are there any questions there?
I have a question.
We did.
Could we put like 1/2 to get rid of the radical, or no?
1/2.
So like 1 minus 3x minus 1 to 2, and then parentheses 1/2.
You mean like rationalizing the denominator?
Yeah.
I mean, you could do a lot to this, but you don't have to. I mean, you could if you wanted to, or you, there's really no conjugate in this case, though. You could multiply the numerator and denominator by this quantity, but beyond that, maybe I'm not understanding. Tell me again what it is that you want to do, Burfin?
Like, can we get rid of the radical, right?
So in order to get rid of it, you can't really get rid of it. The only thing you could do is switch its position in the fraction by rationalizing. But no matter what you do, there's going to be a radical. It's somewhere or another. Yeah, and by the way, since you said that too, I just want to remind everybody, I know I'm always reminding people of this. The square root of a squared minus b squared is not equal to this. I mean, yes, technically this is equal to that, but you cannot split up a sum or difference that's inside a radical. So the square root of a squared is a, the square root of b squared is b, but the square root of a squared minus b squared is not the square root of a squared minus the square root of b squared. Did you want to do that, Burfin? Because that's something people want to do a lot that I have to remind them that they can't do.
Yeah. I was just like trying to see, since we're like simplifying it, maybe like we could get rid of the radical or not, but we just keep it then.
Yeah, just keep it. Most of these answers are going to have radicals in them, and there's just nothing you can do about it.
Okay.
Yeah.
Thank you.
You're welcome. Okay, so this is like a big no. Just going to make sure I put that in there to further emphasize my point. All right, so let's do another one. This will be f of x equals the inverse cotangent of 2x plus 1. And again, your inside function is your u of x. This is just the inverse cotangent of u of x, or u of x is 2x plus 1. So now it's a cofunction, so its derivative is going to be negative. So f prime of x is going to be negative, and then u prime is 2. And then for tangent and cotangent, you're adding in the denominator, and there's no radical. So you're going to be taking 1 plus u squared. It's always a 1 all the time, and then plus, in our case, 2x plus 1 quantity squared. And then we'll just kind of multiply out that binomial to simplify the denominator. So I'll have 1 plus 4x squared, and then 2x and 2x is 4x plus 1. When it looks like we'll actually be able to simplify a little bit more out of this one. So we'll have 4x squared plus 4x plus 2. And then we have a common factor of 2 in every single term. If you have a hard time seeing the canceling, just factor it out of the denominator. You'll have 2 times 2x squared plus 2x plus 1. And then when you cancel out these common factors, don't forget you still have a negative 1 in the numerator. And your denominator is 2x squared plus 2x plus 1. Any questions on B? Now we will do an inverse cosecant of the cubed root of x. Oh, I should probably put a y equals in front of that. Okay, remember that whenever we have radicals and we're trying to take a derivative, it is most beneficial to write your expression with a rational exponent. So we're going to write the cube root of x as x to the 1/3 power. It's cofunction, so its derivative is going to be negative. I'm trying to give you one of each here. In our case, u of x is x to the 1/3 power. U prime of x is 1/3 x to the subtract 1, and you get negative 2/3. And we don't need the chain rule on that one because we're just taking x to the 1/3, not like 2x to the 1/3 or x plus 5 to the 1/3. It's just x. So we'll have a negative u prime. We're going to simplify this quite a bit, actually. Now, remember that with the secant and the cosecant, we have a factor of u of x in the denominator. So for us, that's going to be a factor of x to the 1/3 power. Then we have the square root of, and you're going to switch the order of subtraction from the sine and cosine. It's going to be u of x squared minus 1. And like I said, we've got some simplifying we're going to do. Before I do that, are there any questions here? So we have negative u prime divided by u times the square root of u squared minus 1. Now, notice that if you move this x to the negative 2/3 down into the denominator, you'll get x to the positive 2/3, and then we can actually add those up. So that's going to be my first order of business here for simplifying. So I'm going to, I guess for now, we'll just keep the 1/3 in the numerator. We'll bump that 3 down in a minute. I'm going to move the x to the 2/3 down into the denominator. And then when I do that, the exponent becomes positive. And I still have x to the 1/3. And then in the radical, remember when you take a power to a power, you multiply the powers. A little more work I want to do here. One is instead of multiplying by 1/3, I want to divide by 3. So I'm just going to pop this 3 into the denominator. So the numerator is just going to have a negative 1. The 3 just kind of pops down into the denominator. And then x to the 2/3 times x to the 1/3. Well, when you're multiplying and you have the same base, you add the exponents. 2/3 plus 1/3 is 3/3. 3/3 is equal to 1. So I just have 3x now. And then x to the 2/3 minus 1. I think that this is just fine. I've seen some authors take stuff like this and get real crazy with it. Mostly, I just want to see that you can combine things that should be pretty obvious. Like to me, this is something that needs to be combined. When you see a negative 2/3 in the numerator with the 1/3 in the denominator, I mean, that can be pretty easily simplified. Also, you know, when you're taking a power to a power, that should be simplified. And we shouldn't have a fraction within a fraction. That should be simplified. So these are things that we should be thinking about as we're working our way through. Go ahead, Renee.
So for the, I'm kind of confused on when you got the x 3/3 over 3/3. Why does that equal 3? Why not just like x to the 1 power? And so when you multiplied your x to the 2/3 times x to the 1/3, you got 3 over 3. So
X to the 3/3.
yeah, so why does that equal 3x then?
Oh, it doesn't. The 3 came from here.
Oh, okay.
So instead of multiplying by 1/3, I divided by 3.
Okay.
Because those operations are interchangeable.
All right. I'm sorry. I keep missing stuff like this. So
It's okay. No worries. But do you see why I just have x here?
yeah.
Right from the 3? Okay.
Mm-hmm.
Yeah, so the x came from these two. And then the 3 came from the numerator.
Yeah, I understand now.
Okay. Awesome. Morgan, go ahead.
I don't know if you already explained this, but how did you get x to the 2/3?
Oh, yeah. So for your exponent rules, whenever you are taking a power to a power, which is not the same as multiplying with the same base. When you take a power to a power, you multiply the exponents. So I took 1/3 times 2, and that's where the 2/3 came from. Does that answer your question?
Yeah, I think I just missed a step.
That's okay. You got to ask. Otherwise, like I say, otherwise there's no point in having a synchronous class. You might as well just be learning calculus off YouTube videos. Go ahead, Victoria.
I just wanted to ask, how did you get rid of the x to the -2/3 from the previous step?
From here?
Mm-hmm.
Yeah, so if I want to make the exponent positive, I just have to bump the expression down into the denominator. Anytime I want to change the sign of the exponent, I need to just switch its position in the fraction. So x to the -2/3 is equal to 1/x to the +2/3.
Oh, so you just combine them pretty much into one. Okay.
Right, yeah. So instead of, I guess instead of doing the whole thing in the numerator as a complex fraction, I just consider this to be my denominator.
Okay. Okay, cool. Thank you.
You're welcome. Usan, go ahead.
I was wondering why you took the 3 from the -1/3 from the numerator and put that into the denominator.
So remember that when you are multiplying, well, when you have a fraction, I'm going to say when you're multiplying fractions, but that's not really the case. If you're multiplying by 1/3, you're dividing by 3. So like, let's say if I take a quantity like 1/3, and I multiply it by x, what I'm really doing is I'm just dividing x by 3. So instead of thinking about this as taking this whole fraction, because really I could have taken this 1/3 out front and said, okay, well, I'm just going to take 1/3 and multiply it by the whole thing. But instead I just said, okay, let's bump this 3 down into the denominator. If you wanted to think about it the way that we've done with simplifying complex fractions, you could just multiply the numerator and denominator by 3. And if you did that, you would be multiplying here by 3 and here by 3, and those 3's would cancel, and that's where that 3 would have come from down here. So if you want to kind of think about it that way, think about it that way. Does that help?
Yeah, that helped me out.
Okay. Excellent. I'll leave that there in case someone likes it. Okay, anyone else on this one? Wonderful. Let's go ahead and do the inverse sign of e to the -x. If you find it helpful to take the function out as u of x, you could say, okay, fine, we'll let u be e to the -x. I should probably call it u of x just to match what we've done in the formulas. So that's your inside function. And then u prime is going to use the chain rule. So it's e to the -x times the derivative of the inside function. So it's -e to the -x. Hopefully you're going to take the derivative of e to the -x so often that you're automatically going to think about it as -e to the -x. That's my wish for you. So there's your u prime. This is what's going to go in your numerator. So the derivative for the inverse sign is u prime divided by the square root of 1 minus u squared. So here's your u prime divided by the square root of 1 minus u squared. And I'm not going to do a whole lot to this one. I'm just going to take e to the negative x and square it by taking the power to a power and multiplying the powers. This is another one where you'll see some authors will really go crazy with the simplification. I'm not too worried about it. I just want you to use your basic exponent rules when you can. So it should look like that. And I think this is really good. Any questions on D? E. I might need a little more space. H of x is equal to x squared times the inverse tangent of 5x. Now notice that this time I didn't just give you an inverse trig function. I multiplied that by x squared. And that means you're going to have to use the product rule. You're taking the product of a polynomial and an inverse trig function. So you'll let your polynomial be f, and your inverse trig function will be g. You know, I thought on the test, for the most part, people seem to have a pretty good grip on when they needed to use the product rule, which is good. I find that sometimes students just don't know when they need it. And they just they'll take the derivative of x squared and multiply it by the derivative of inverse tangent and be like, I'm done. But you can't do that. You can't just take the derivatives and multiply them. I did see that from time to time on the test, but for the most part, it seemed like people were using the product rule. So that's good. F prime is 2x. G prime is going to be the derivative of the inverse tangent of 5x. Now, if you want to get crazy here and label u of x as 5x, that's fine. But I think I don't want to get too crazy with the notation. The derivative of the inverse tangent of u is u prime, which in our case is going to be 5, divided by 1 plus u squared. The whole quantity. So don't take 5x squared without putting parentheses around the 5x. It does make a difference. We're going to rewrite it because we're going to want it to look nice. 5x quantity squared is just 5x times 5x. So you also have to square the 5. So 5x times 5x is 25x squared. All right, so let's go ahead and use the product rule then. Are there any questions on f and g and f prime and g prime before we do that? So we're going to take f prime times g plus f times g prime. And there's not a whole ton we can do here to simplify. One thing I do want to point out that I'm worried that you might do, and I saw a couple people do it on their test, is that you can't cancel out the x squareds here and here. You can't do that because you can't factor it out. You don't have an x squared in 1. If you can't factor it out, you can't cancel it out. So don't do that. But we can just rewrite this. The first term is just going to stay as is. But the second term, I'm just going to multiply the x squared into the 5 in the numerator. And then the denominator, just leave it alone. I used to make students write these all as one fraction. I don't do that anymore. It was just a lot of time I was spending on doing stuff that wasn't that important. Okay, questions on E? F is h of x equals the sine of the inverse cosine x. Now this one's kind of tricky. It's not like it's a lot of steps. It just looks tricky. It's one of those very subtle things that your mind doesn't want to accept. Because you're taking the sine of an inverse cosine of x. You're lucky that I didn't make this like x plus 1, or I guess x plus 1 wouldn't have made that big of a difference. But it could have been like the square root of x. And that would have been more of a doozy. When I need doozies today. Okay. Okay, so notice you're going to need the chain rule. You're going to take the derivative of the sine as though you have sine of x. But then you're going to chain on the derivative of the inside function. Okay, so here we go. Ready? The derivative of sine x is cosine x. So the derivative here is going to be the cosine. Leave the inside function the same. Chain on the derivative of the inside function. So the derivative of the inverse cosine of x, well, it's a cosine, so it's negative u prime. U in this case would be x, divided by the square root of 1 minus u squared. So if you want to label this u of x equals x to match your formulas from earlier, that's fine. I find that helpful. Okay, so this is what we obtained using the chain rule. So we took the derivative as though we just had sine x. So we got cosine, left the inside the same, multiplied by the derivative of the inside function. Now we're going to simplify this. You learned this in trig, but maybe you don't remember it. It's kind of like how you take x times its inverse, which is 1 over x, and you just get 1. The same sort of rule applies here. The cosine of the inverse cosine, it's kind of like they cancel out, and you just get the x. It's like when you take e to the natural log of x, or the natural log of e to the x, that sort of thing. Anytime you take a function and compose it with its inverse. So we're going to simplify this expression to just x. So we have x times, and I'm going to write this in 2 steps instead of 1. And again, this is from trig. If you don't remember it, I'm reminding you now. And we'll simplify this to negative x divided by the square root of 1 minus x squared. There's your derivative. You actually learned how to rewrite these in trig using triangles. I don't know if I want to get into all that though. You can always ask me about it if you want to know later. Okay, questions on F?
I just wanted to ask, could this have been done using product rule too?
Not that I'm aware of, because you're technically not multiplying a sine by anything. I mean, it would be different if you had sine x.
Oh, okay. Yeah.
You know what I'm saying?
Yeah.
But you're taking the sine of, and then this is your angle in this case.
Okay,
Yeah.
yeah, that makes sense.
I'm really glad you asked that, though, because I didn't even think about the fact that that might be confusing. So I'm really glad you brought that up. Yeah, so note the difference between sine x times inverse cosine x. This would need the product rule. And it's not the same thing, and it looks very similar, but it's not the same. Okay, other questions on F? So what we're going to do next, I have two examples for you. They're a little bit on the long side, but they're the last ones I have in this particular section. And they are about taking derivatives implicitly for inverse trig functions. Wouldn't want to leave that out. And those are going to come back in 3-4 also. So you're going to be applying the chain rule and implicit derivatives and everything else in each of these sections, so that you know how to work with all kinds of functions. Differentiate implicitly to find the equation of the tangent line. And I didn't want to just say differentiate implicitly. I wanted to make it a tangent line problem because I really want you to get used to evaluating these at the given point, especially if you end up having an inverse trig function in your derivative, which isn't always going to be the case. You do have it in B. All right, so A is going to be the inverse tangent of x plus y equals y squared plus pi over 4. And we're going to look at this at 1, 0. Now, I gave you formulas that were for inverse tangent u of x. This is technically u of x and y. So if you just want to call it u, that's fine. If you want to call it u of x and y, that's fine too. You'll see that notation later on down the road, especially in Calc 3 as you start to work with more variables. Okay, so we're going to take the derivative here. For the inverse tangent, I need to take u prime over 1 plus u squared. So u prime is the derivative of x plus y. The derivative of x is 1. The derivative of y is dy dx. And this is the first time I can remember us doing an implicit differentiation problem where we have a fraction where we have dy dx in one part of the fraction. So this is new. So this is u prime divided by, and then in the denominator, we'll do the 1 plus u squared. So we'll have 1 plus x plus y quantity squared. And I think another confusing thing about this is students are like, wait, we took a derivative and it was with respect to x and y. Do we need to tag on another dy dx? You already have a dy dx here. That is sufficient. You don't need to put another one on there. You only took the derivative when you took the derivative of u. So you tagged on the dy dx. That's all you had to do. In the denominator, you didn't actually take a derivative. You're good. But you will need the dy dx on the right-hand side when you take the derivative there. And don't forget that pi over 4 is a constant. I know when we see symbols, we tend to think of them as variables, but it's pi. It's a number. So don't worry about thinking about having to take a derivative of, like, I don't know, 1/4. It's 0. The derivative of any constant is 0. Okay, so this is the hard part. I already did it. Does anyone have a question here? Because if you're going to have questions, it's probably here. Go ahead, Busan.
Where did you get the 1 plus dy dx in the numerator?
So that came from taking the derivative of this function u of x and y. So the derivative of x is 1, and the derivative of y is dy dx.
Oh, I see.
I'm glad you asked. Other questions? Okay. Thank goodness. My husband's out there mowing the lawn and it is so loud, but I think he's finally done with the front. It's just raining all the time. It's like it has to be mowed like every 3 days. It's really distracting. I don't have this problem in a regular classroom. Lawn mowing problems. Okay. Here's what we're going to do. We need to solve for dy dx. So that means we're going to need to get all the dy dx's together and all the non-dy dx's together. With this fraction, this is problematic. We don't like it this way. We can't get the dy dx by itself while it's with another term in the numerator. I can't factor it out because I don't have one to give here. It's not done. Yay. So what we're going to do, I'm going to rewrite mine. Anytime I rewrite mine, I suggest you rewrite yours just because I don't want you to look at your notes later and wonder where things came from. That's why I rewrite stuff, because otherwise, if I mess with this, it looks like I originally had things there that weren't there. To solve this equation, I need to get rid of this fraction. Anytime you're solving an equation that's a fraction in it, we want to kind of split that up and undo the fraction. To undo the fraction, we're going to multiply both sides of the equation by our denominator. So if you want to think about it as cross multiplying, think about it as cross multiplying. But if you want to just kind of multiply both sides of the equation by this quantity, I mean, essentially that's what we're doing. Be careful with your grouping symbols, like make sure you have some. And then you can cancel out the 1 plus y squareds on the left. Now, on the left, that's kind of nice for us because it just leaves us with 1 plus dy dx. But on the right, we're going to have to we're going to have to distribute this quantity into the parentheses because I have more than one term that I'm multiplying by. Before I continue, does anyone have a question about what I've done so far? Remember, whatever you do on one side of an equation, you must do to both sides. So I haven't changed the equation because we just took the entire equation and we multiplied each side by the same quantity. That allowed us to get rid of the denominator on the left-hand side. All right, so now on the right-hand side, I'm going to multiply first by 1 and then by x plus y quantity squared. So when I multiply by 1, I'm just getting my exact same expression back for the first term. For the second term, I'm going to pop my dy dx on at the end. So I have 2y times dy dx times x plus y quantity squared. Okay, questions there? So now I have the dy dx's each in their own terms. So I have one of the terms here, here's another term, there's another one. But I only have one constant. It's just 1. So what I'm going to do is I'm just going to subtract this dy dx on both sides. And that's going to leave me with 1 equals 2y dy dx plus 2y x plus y quantity squared dy dx minus dy dx. Now you can go ahead and factor out the dy dx and solve for it. I still have 1 on the left. On the right, I'm going to take that dy dx and factor it out. And what I have left then on the inside of my parentheses is 2y plus 2y times x plus y quantity squared. Don't forget you still have a minus 1 here in the last term. Now to solve for dy dx, I'm just going to divide both sides by this factor. So we'll have dy dx equals 1 divided by 2y plus 2y times x plus y quantity squared minus 1. Okay. Questions on dy dx? Go ahead, Morgan.
Why didn't we FOIL the x plus y?
I see why this is confusing because I made you do it when I was having you find inverse trig derivatives. Really, the goal here is to find the equation of the tangent line. So I'm going to use this to get to a slope. I'm not as concerned with how simplified it is. I do want you to simplify it. But I guess for something where there are so many steps, I'm less concerned about like multiplying out a binomial. I see how that's confusing.
So like if we did it, would we get the wrong answer or?
No, you could definitely write this as x squared plus 2xy plus y squared and multiply that by 2y. But since all we're really going to do is evaluate this at the point 1, 0, I feel like that you're opening yourself up to having a lot more errors if you end up getting into this, I don't want to say algebraic mess, but you're getting into more work than you would have to do in that case. I mean, you could FOIL it out, but you don't have to. Does that answer your question?
Yeah, it does. Thank you.
Okay, any other questions before we find the slope? All right, so let's look at this at the point 1, 0. Everywhere we see x, we're going to substitute 1, and everywhere we see y, we're going to substitute 0. Uh, 0 plus 0 minus 1 is -1. 1 divided by -1 is -1. So that's your slope. And then to find the equation of the tangent line, we'll just take y minus y sub 1 is m times x minus x sub 1. And y equals -x plus 1. This is another one where if you really wanted to, you could graph it on Desmos and put the, also graph the tangent line equation and verify that you do indeed have a point that's tangent at 1, 0. And this is the line that would run tangent through that point. I'm going to do one more of these. Are there any lingering questions on this one? So B, x squared plus x times the inverse tangent of y equals y minus 1. The point is negative pi over 4, 1. All right, so let's go ahead and take the derivative. If you want to kind of scan it over and get a good idea, you're going to need the product rule here. So since you already know that, if you want to list out the pieces, if you find that helpful, that's fine. I saw a lot of you guys labeling F and G on your test, so it seems like you probably do find that helpful. It never hurts to write more steps, so maybe I'll go ahead and do that before we officially take the full derivative. All right, so I'm multiplying one function by another. That's product rule. F prime is 1. G prime, and remember here when you're taking the derivative of G, G includes the variable y, so it's going to need a dy dx on it. The inverse tangent will be u prime, which in our case is y prime, which is dy dx, divided by 1 plus u squared. So again, with the notation, in this case, u of y would be y. So we took u prime, which is dy dx, and divided it by 1 plus u squared. And you've got your dy dx in there, so you're good to go. Now, when we use the product rule and we take f prime g, remember that g does not get a dy dx tagged onto it because g is not g prime. If you're not actually taking the derivative of g, then you don't pop it on there. Okay, so the derivative of x squared is 2x. Now, here's where the product rule is going to come in. F prime g, well, f prime is just 1, so I'm not going to write it. F prime g is 1 times the inverse tangent of y. And again, I'm not putting a dy dx on here because it's f prime g, not g prime. F prime g plus f g prime. So I'll label this G prime. This whole thing is f prime g. And on the right-hand side, the derivative of y is dy dx. The derivative of 1 is 0. Questions on the derivative? This is probably the hard part. Wonderful. This is weird because of the way it's written, but note that there's actually nothing to really distribute here. You're just multiplying x by this quantity. So what I'm going to do is I'm just going to rewrite this fraction so that it looks a little bit more clear as to what we need to do with the term. I'm not actually going to change anything. I'm just going to maybe scoot this 1 plus y squared over, and then I'm just going to multiply by this dy dx. So these two expressions are equivalent. They're just written slightly differently so that we can see that dy dx is sort of tagged onto that term. It's really just for clarity. But now we can see that we have two dy dx terms and two non-dy dx terms. So I'm going to leave the two non-dy dx's on the left, and I'm going to move this one over to the right. So 2x plus the inverse tangent of y equals dy dx minus x over 1 plus y squared dy dx. Now you're going to factor and solve for dy dx. Two x plus the inverse tangent of y equals, I'm going to factor this out. Don't forget, when you factor it, you still have a 1 for your first term. And then when we solve, we're going to divide both sides by 1 minus x over 1 plus y squared. Okay, now officially, by the way, this is not simplified because it contains a complex fraction. All I've asked you to do here was find the slope, find the equation of the tangent line. On your test, I'm going to actually ask you to make sure that dy dx is simplified. So for good measure, we're going to simplify the complex fraction. It's good for us. So I'm going to rewrite it and leave a little space on both sides. And I'm going to multiply each term by the LCD, which is the only subdenominator that you see. So we're going to multiply in each term by 1 plus y squared. And this is just to get rid of the complex fraction. I kind of want this to be an equal sign. Now, the whole point of that was so I can get rid of this denominator that's causing me problems. And you might get done with this and say, really, it looked better the way it was before. What can I do? What can I say? You can leave it factored, though. There's nothing wrong with that. Or you could just factor out the 1 plus y squared and then just leave the rest of it as a separate factor. If you want to do that, there'll be less work that you have to do multiplying everything out. Because really all you did was you just multiplied this whole numerator by that quantity. So the minus x comes from your numerator. I'm sorry, the numerator of the second term of your denominator. And then the 1 plus y squared is from the first term of your denominator. And this, I would say, is fine. Don't worry about getting too crazy here. There's no complex fraction. That's mostly what I was wanting to avoid here. Go ahead and evaluate this at your point, which is negative pi over 4, 1. This one is a little bit. Okay. So dy dx is 1 plus y squared. 1 squared is 1. Twice negative pi over 4 plus the inverse tangent of negative pi over 4 divided by 1 plus 1 squared minus negative pi over 4. Kaylin, what's your question?
For the why is it negative pi over 4 in the tan x? Or tan,
Oh,
yeah.
you're right. Why is it? I don't know. That's a good question. Thank you. It should be 1. You're right. You know why I did that? Because I knew that the tangent of 1 was pi over 4, and my mind did like a little flip. Thank you, Kaylin. Did I do that anywhere else? I don't think so, because I almost did it a couple places and I had to stop myself.
I have a question.
Yeah, go ahead.
Can you go to the beginning of this?
C.
Okay. So you did F as X and G was tan, the inverse, and U is Y. And under it, you did 2x plus tan, but isn't it like F prime is 1? So wouldn't you put like 1 and just U there?
Well, it's F prime G, and G is the whole inverse tangent of Y. So since F prime was 1, I just didn't write it. I mean, you could have written it. But G is your entire inverse tangent Y.
Oh, okay.
Was that your question?
Yeah, with the 2x, it's like kind of seems like we already have like 2 of them. So I kind of missed the, okay, I got it.
Oh, okay. Okay, I see what you're saying. Cool. Okay, other questions on this one before we proceed? All right. 1 plus 1 is 2. 2 times negative pi over 4 is negative pi over 2. And then plus the inverse tangent of 1. Okay, so you're asking yourself what angle. I'm going to write this off to the side. Technically, you can put this into your calculator, but you're asking yourself what theta has tangent theta equals 1. That's what you are asking yourself when you're looking at an inverse trig function. We kind of talked about these on the pre-algebra review the first week of class, but that's what an inverse trig function is. You're looking for an angle. So the tangent is 1 whenever the sine and the cosine are the same, because remember, tangent is sine over cosine, and a value over itself is 1. And that occurs at pi over 4. So we're going to write down pi over 4. Now, if you put this in your calculator, it's not going to tell you pi over 4. It's going to give you the radian approximation. By the way, I totally forgot to mention this, but some of you guys on test 1 were giving me all kinds of crazy answers for, there was like a trig problem where I asked you to find the limit numerically. And it's possible that you had your calculators in degree mode. Make sure that your mode is radians, not degrees, especially if you're borrowing your calculator first from someone else. So inverse tangent 1 is like approximately 0.785. If you're not sure if that's pi over 4, but you think it is, just enter pi over 4 and get a decimal approximation. And if you get the same digits, it's pi over 4. That's one that we should remember pretty well from trig because we used it all the time. All right, in the denominator, I have 1 plus 1 plus pi over 4. And we are going to simplify this. All right, negative pi over 2 plus pi over 4 is negative pi over 4 divided by 2 plus pi over 4. I'm just sort of simplifying this in pieces. And now here I am trying to get to my slope, which is going to be negative pi over 2 divided by 2 plus pi over 4. And it's kind of up to you how simplified you feel like this needs to be in order for you to write your equation. You might want to go ahead and simplify the complex fraction by multiplying each term by 4. And if you do that, you get negative 2 pi divided by 8 plus pi. And there's your slope. This is another one that WebAssign would accept some crazy answer for. Y minus y sub 1 equals m times x minus x sub 1. You guys have done a ton of these. Do the best you can with this one. Don't get super crazy. Just solve for y. I'm going to distribute. When I multiply this by pi over 4, let's see, I'm just going to do this first. Maybe I'll do it like that. And then we'll simplify a little bit more. So we have minus pi squared over 2 divided by 8 plus pi. And this is another instance where I'm going to pop that 2 down into the denominator. Pi squared divided by twice 8 plus pi. And then just, you know, add 1 on both sides. You don't have to get super crazy with it. It already looks super crazy. Don't feel like you have to distribute here. I'm not like super hung up on this. The nice thing is you could check it online, verify that that is indeed the equation of the tangent line. Yep, negative pi over 4, 1. I would not put anything this involved on the test. I like to do a problem like this in class just because it incorporates so many algebraic techniques. It incorporates some trig techniques. It incorporates your inverse trig derivatives, your implicit derivatives. I mean, there's a lot that's jam-packed into this particular example. All right, so that was 3-3. I'm going to start 3-4. If you have questions on this one, I'm giving you a few more seconds to keep looking at it. I know sometimes it takes us a minute to develop our questions. Oh, you guys, time just flies in this class. For me, anyway. I know, not for you, but for me it does. Because I love it so much. Even though I have to sit around at home. It could always be worse. All right, 3.4, last section for chapter 3. I'm going to start it now, finish it at some point tonight / early tomorrow morning. 3.4. When it's up, I'll send you an email, by the way, so you'll know. Derivatives of logarithmic functions. I also want to remind you of some log rules because we are going to need to simplify some of these before we take the derivatives. And sometimes we don't have to, but it makes our lives a lot easier if we simplify the expression first. So let me give you those first. These are from Algebra 2 or college algebra. You saw them at some point. I'm going to use a natural log when I show you these rules, but they apply to a logarithm of any base. First of all, I want to remind you that the natural log of x is the log base e of x. So it's just the log of x with a base of e. That's why it's special. So we're going to be working with some logs that have bases other than e, but a lot of the logarithms we deal with in this section are going to be natural logs. Okay. If you just see, oh, I should remind you of this too. Log x, it's log base 10 of x. It's just assumed that the base is 10 if it's not written. If the base is something other than 10 or e, it'll be written in your logarithm. So you might see like log base 3 of x. Well, there's no other way of writing that. They have to write a base of 3. But these are the two special ones. This is called the common log because it's a base 10. And this is called the natural log because it's got a base of e. So your rules here are, I'm going to use a natural log to show them. I don't remember what variables you learned these with. They change probably every book. The natural log of some real number to the p power, you can rewrite by bringing the power out front and multiplying it by your logarithm. So this is a rule that we're going to use from time to time. You had a rule for the log of a product. If you were taking the logarithm of some product a times b, you could rewrite that as the natural log of a plus the natural log of b. And I want to say here, note, the natural log of a plus b does not equal the natural log of a plus the natural log of b. This is an extremely common algebra problem. It's like when you try to take the square root of a sum and split it up into the sum of 2 square roots. You can't do that either. People try to do the same thing with logarithms. This is represented by the logarithm of a product. Can't split up the sum of the sum inside a logarithm. We have the same or a similar rule for quotients. We would say that this is the natural log of a, and this time you're going to subtract. It'll be minus the natural log of b. And same thing, I should say plus or minus in this case. There's no use in writing it twice. In either case, that will not work. You have special rules for the logarithm of a product and the logarithm of a quotient. All right, so I'm going to give you the rules here for these derivatives for log functions, and then I'm just going to give you a bunch of examples using different kinds of functions. Some of them we'll have to rewrite, some of them we won't. Some of them will require the chain rule, some of them won't. And then towards the end of this, you're going to be working on implicit differentiation using logarithmic functions and what else? Finding the equations for tangent lines, stuff like that. so these are sort of your log rules from algebra. So first, I'm going to give you two definitions. One of them is just for the derivative of a general log function. Derivative of a log function. The derivative of y equals log base a of x. Now, remember that for a logarithm, whatever this quantity x is has to be positive. You can't take the log of a negative number. And your base has to be positive and not equal to 1. These are just rules for logarithms from algebra. But your derivative is y prime, which is d dx of log base a of x. Now, of course, a is just some real number here. It could be a 3. It could be, technically, it could be e. But I'm going to give you a special rule for that. Could be 10. It's just going to be 1 divided by x natural log a. Usually we write the natural log with a cursive L. You don't have to, but it keeps it from looking like you have 1n instead of ln. We can expand this. Instead of just representing a function x, we can represent any function u of x. So we'll do that next. So we'll say the derivative of the log base a, not 9, it's definitely an a, of u of x is going to be u prime of x divided by u of x times the natural log of a. Okay, we're not going to use these particular rules a whole lot, so you might not remember them. For natural logs, you're going to use them so often, I would think you would memorize them. These you might want to highlight just so that you can find them if you need them, because I don't remember these half the time. I don't use a lot of logs with a base other than e. I also have a note here, and I do think it's probably going to pop up in this section, so I want to make sure I mention it. You learned in 3.1, it was at that point in the video where my power went out. It was really close to the end. The derivative for an exponential function with a base that wasn't e. And I think it's going to pop up here again, so I wanted to remind you of it. The derivative of a to the u of x. You didn't use it a whole lot, so I want to make sure we mention it here. Is a to the u of x times the natural log of a times du dx. So if you see that pop up here, looking for the derivative of some real number to a function of x power, just wanted to remind you of that rule. Oh, you know what? I did have a note up here about this power rule for logarithms. And I kind of feel like I want to include it up here where I had the like notes, don't do this thing. I also want to say that the natural log of a to the p is not equal to p times the natural log of a. So this only works if the p is being applied directly to a, not to the entire logarithm. The parentheses make a huge difference here. So if you see the natural log of a being taken to a p power, you can't bring the exponent down. That rule doesn't work that way. So little warning there, because I think you might be tempted to do that if you see such an expression. Now, as far as your natural logs, we have more specialized derivatives because you see these all the time. The derivative of the natural log function. the derivative of y equals ln x. Now x has to be positive, otherwise it's not in the domain, is y prime equals the derivative with respect to x of the natural log of x is 1 over x. So if your function is natural log x, its derivative is 1 over x. If you're lucky, otherwise you're going to get natural log of some function of x, and you're going to need to use the chain rule. No big deal. So let's say you're taking the natural log of some function u of x. That derivative is going to be u prime divided by u. And you're going to use that rule all the time. You can still put a box around it if you'd like. But this one is one that you're going to be just using constantly, constantly, constantly. Natural log u of x. All right, so we have the rules down. Let me start with some examples. Don't have time for a ton, but we can still get your feet wet. Find the derivative. So our first one is going to be f of x equals the natural log of 4x. Now, some of you are going to think about this as taking the natural log of some function u of x, and other people are going to see this as taking the natural log of a product. Now, we have a rule that allows us to break this up. I want to show this to you both ways. A lot of times, if we can break this up, it's easier to do so. So if you are thinking about that and you want to rewrite your function using this rule, note that in this case, we do have a product. We have the natural log of 4x, which means we have the natural log of 4 times x. That's a product. We can split it up. So we can rewrite this as the natural log of 4 plus the natural log of x, and that's using your product rule for logarithms. Now, note that we didn't actually take a derivative yet. All we did was we rewrote the function to make the derivative easier for us to find. Now, the natural log of a constant is also a constant. You can always put that in your calculator if you're not sure. The derivative of a constant is still going to be 0. So when you take your derivative here, you'll get 0 plus, and then we said that the derivative of the natural log of x was 1 over x. I gave you that in this rule. So we're looking at the natural log of x. Its derivative is 1 over x. That means that our answer in this case is 1 over x. And you might be wondering, like, well, what happened to the 4? Doesn't that matter? No, it does not matter. Another thing that drives people crazy is, just like with inverse trig functions, they have a really hard time understanding how we started out with a natural log and we ended up with no natural log. They're like, wait, what happened to the natural log? I don't understand. My answer doesn't have one in it. I must have done something wrong. Most of the time, when your function involves a natural log, your derivative will have no natural log in it. That's okay. Accept it. It is what it is. It's not wrong. I mean, it could be wrong for other reasons, but not for that reason. Now let's say you didn't think to split this up and you use this as natural log 4x. I'm rewriting the problem now. So this is the alternate method, I should say. So if you didn't think that you had the log of a product, you just didn't think to split it up. That happens too. You're going to let u of x be equal to 4x. And you're going to think about this as f of x equals the natural log of some function u of x. Like half the students will do it one way and half the students will do it another. I don't always like to show alternate solution processes, but because students are so random with how they do these, I like to do both. I gave you a rule that said that the natural log of some function u of x is u prime over u. So to take f prime, you're going to take u prime, which is 4, divided by u, which is 4x. Now, if you did it that way, you'll notice that now you can simplify your derivative because 4 over 4 simplifies to 1, and you end up with f prime of x equals 1 over x, which is the exact same thing we got before. So you decide. In this particular instance, I don't think one method was necessarily any faster than the other. In some instances, it's going to make a huge difference to your solution process. If you don't break it up, you might end up in a giant mess. So we're going to do lots of expanding of logarithms to rewrite them using our algebra techniques to make our life a little bit easier when we take the derivative. Are there any questions on A? B is f of x equals the natural log of x squared. Now, if you recognize this one as being the natural log of a to the p, then you can rewrite it. I gave you a rule that said the natural log of a to the p is p times the natural log of a. In this case, that will simplify your life. The natural log of x squared is twice the natural log of x using the power rule for logs. So you took natural log x squared and you rewrote it as twice the natural log of x. Now you can take its derivative. The constant multiple rule still applies. You'll have twice, and then the derivative of the natural log of x, we said was 1 over x. We don't have a function u of x in this case, we just have x. And your derivative is just 2 over x. Go ahead, Morgan.
Doesn't the 2 go to 0?
Well, you're not adding them. In this case, it's just a constant multiple. If you had 2 plus the natural log of x, then it would go to 0. But because it's a constant multiple, it just kind of tacks on to whatever your derivative is. So it does make a difference in this case. Does that answer your question?
Yeah, so you pretty much just like rewrote it in the 2 times 1 over x. Like you didn't do any like derivatives or anything, you just rewrote it?
Oh no, so this is the derivative.
Okay.
The rewrite was when I rewrote it as twice the natural log of x. So these two expressions are the same. And here's where we took the derivative. So this 2 came down as the constant multiple, and the derivative of the natural log of x is 1 over x from the rule on the previous page. which we also used up here. Does that answer your question, Morgan?
Yeah.
Okay. Other questions on this one? Okay. Now, if you didn't think to use the power rule, that's fine. You could have said alternatively, let u of x be x squared, and then you're looking again at the natural log of u of x. And then you would have said that f prime of x is u prime divided by u. Which simplifies to 2 over x. So same exact answer, different solution process. Personally, I like this one because it doesn't involve any usage of the chain rule, which is officially what this is. Just given to you in using a formula. All right, I'm gonna do one more, and the rest of it I'll leave for later, like tonight for me. This is going to be the natural log of x cubed minus 4. And I want to make a special note that this does not equal the natural log of x cubed minus the natural log of 4. It does not work like that. You don't have a rule for the log of a sum or difference. There's nothing you can do here to simplify this. It's already simplified. So I'm going to say already simplified. We cannot rewrite this. So you're just going to have to take the derivative the old-fashioned way. So I'm going to use the rule that says that y prime is going to be equal to u prime over u. So if you'd like, go ahead and write your function u. So for the natural log of u, we'll have u equals x cubed minus 4, your inside function. And then u prime is 3x squared. Now for your derivative, y prime is going to be equal to u prime over u. If you like the x's, I'll pop them back in there for you. U prime over u is 3x squared divided by x cubed minus 4. Stick a fork in it. So like I said, if you feel like, oh my gosh, my answer doesn't have a natural log in it, that's fine. Most of the time it won't. You're just taking u prime over u anytime you're taking the derivative of a natural log function. All right, this is all I have time for right now. I will finish this out asynchronously. My examples go through L. Some of them are shorter than others, but none of them are like a whole page long. And then we'll do equations for tangent lines. And then we'll do some implicit derivatives. Yeah, we might skip the logarithmic differentiation. Nah, I could live without it. Some years I do skip it. Maybe this year would be a good one to skip. We'll see how tired I am later. All right, well, you guys, I'll put up some homework for this. Whatever I assign from 3.3, 3.4 will be due on Wednesday, as stated previously. Email me if you have questions. I'll let you know if I can pop into an office hour on Tuesday. I know that some of you will show, so I certainly don't mind making the time for it. You guys have been really good about asking questions. But have a good weekend. Get cracking on the homework. Your test is on Wednesday. And I will not see you Monday. Don't come into our meet. You don't have class Monday. Good night.